I want to thank our sponsors first. We have two sponsors that are helping us put on these lectures. We have Abe's Appraisal, and we have Hammond Lumber Company. So we're really grateful for both of those. But also, this couldn't happen without all the volunteers that help. And I want to just take a second to thank those. We have Margaret Hayter and Pat Porter, who serve on this committee with me, and we plan all year, and we'll start talking about next year's soon. So if you have ideas you want to share with us, we have some clipboards running around, ideas for other lecturers or people that you think would be a good lecturer. Please let us know. In fact, this lecture is a result of a survey we did last year, and somebody said, I want to hear about geology, so here we are. All right, so now on to tonight. I want to thank Shelley Gallagher, she's the director of Bristol Parks and Recreation, for recommending Henry and Steve to us. They came down to look at what the storm damage did there, and she said, you have to have these guys do this lecture for you. And it's obvious because between them, they have 80 years of experience in geology. How could we get anybody more? You know, this is amazing. They're wildly experienced in geology in general, but about this coast, which obviously everybody has an interest in. And it's very special to us all. So they have, I think you've probably noticed, they've put a map up on the wall for you to see, but also, yes, thank you. And also, there are some handouts there, which they wish you would take, and there are more things on their website, so please check that out too. So they're gonna talk about how those beautiful rocks at Pemaquid were formed, how they've changed over time, and how they're going to keep changing. So please welcome Henry Berry and Steve Dickson, and they're going to talk one at a time. So is it you first? Okay. This is your backup.
Dave's on the sound, and he's also recording this, and they said, is that okay if we record it? And I said, yeah, because this is a non-profit organization, and I just, for anybody that's listening to it after the fact in the recording, remind you that this is for personal use only, non-commercial, right? Because we're a state organization. All right, so I want to say that. We got 500 million years to go through here, so it may take a minute. So be patient. Geology of Pemaquid and the Maine coast. Well, we'll see what we can do. So how many people here have been to the Pemaquid Point Lighthouse Park? All right, that's a good start. Now, when you go to this very special place, it really is an individual experience because you relate to this place in your own way. You bring whatever experience you have to this place. So you see what you want to see. And I want you to look at this photograph for just a minute. This is a photograph, okay? And I'm going to ask you in a minute to make believe you're an 8-year-old so that you don't know anything geological. That's going to get in the way, all right? But I want you to see how many different things you can pick out in this picture. How many different things are there, all right? And just like one-word answers. How many different things are there in here? Just look, just look.
Water. White lines. Loose boulders. Like seas.
So you're like 8-year-olds. You're answering before I told you to answer. So that's great. I love it. Because 8-year-olds have enthusiasm and they don't worry about being right and wrong. All right. So now I can hear some of the answers. So what do we see here? I'm trying to use this little laser pointer thing. All right. So who said lighthouse and buildings? Nobody. Okay. I heard rocks. All right. You got to be more specific. I know quartzite is too, it's like,
Igneous.
white rocks. Some dark striped rocks. Some loose boulders over here on the ground.
People.
People up here walking on this, yeah, ridge of white rock, right? Tower, did I hear? Power. Yeah. Someone said water. Yeah, there's water down here.
Trees.
Trees, okay. Sky.
Poison ivy.
So this is what I thought of before we came here. All right, lighthouse, buildings, trees, yeah, loose rocks. Did you see this curved shape here? Shapes. All right. Now, a lot of artists go to this place, and when an artist tries to depict a scene, they try to show you what they are seeing. And a lot of artists go to this very same place and they see different things. So here's just some things that I found online, and these are all on the internet, so they've been posted online freely by these artists for us to see. So I just want you to see what they want us to see. David Shirer. Renee Lammers. These are the artists. Ronald Bossy. Kathleen Horst. Edward Hopper. Yeah. There's no rocks in there, by the way. You notice that? Okay.
There are in the White House.
Ron Quinn. Liz Von Borden. Michael Meisner. Tricia Clark. They've all been to the same place, right? And they see different things. And that it's not right or wrong, right? It's just what they want us to see. So that's kind of where I want to start. I'm a geologist, and so I'm going to show you some of the things that I see when I go here. Right? It's not maybe what you see. That's okay. So I'm going to focus on a few of the things that we picked out on this photograph. I mean, all of that stuff is in the photograph. First are the striped rocks, and I'm numbering them 1, 2, 3 because that's about the extent of my artwork capability. But they're also in a particular order. 1, these striped rocks. 2 are these white rocks. There's some blobby ones down here. There are also some white ones up here on this ridge. And then 3 is this curved shape. Okay, so the striped rocks first are probably the most obvious thing, but it's what we walk across there. And those are thin layers of fine sand and silt that were deposited in an ancient ocean basin in the Silurian period of geologic time. That's what that is. Just layers of sand and silt piled up. They're tilted out. They're not horizontal anymore. And we map this as the Bucksport Formation. You can trace it all the way up through Belfast up to Bucksport. It was named after Bucksport because that's the first person that wrote it down, said Bucksport Formation a long time ago. And said, oh, well, it's the same thing down here. Okay. recently we discovered that there's a little layer of volcanic ash in it. It's up in Bremen, Greenland Cove, in among the sand and the silt. That's pretty exciting to us. Those little white spots in there, those are little minerals that were erupted out of a volcano, and we've managed to date it at 423 million years ago. Plus or minus 4. I mean, we can't be too, you know. I mean, that's pretty good for us. This is the old Bristol Historical Society, right? Plus or minus. The second thing I wanted you to notice when you go down there next time are these white rocks, and these are younger. You see, it cuts right across those layered rocks. The younger igneous rocks, like this one, intruded as molten magma under the earth. That's what igneous rocks are. They crystallize from molten rocks, molten magma. And fine-grained ones like this one, look at it, cuts right across everything. That's a granite. And there are coarse-grained rocks, ones with big minerals on them, and that's 6 inches across, that big feldspar grain. These are called pegmatite. That's the state rock, if you didn't know that. Your legislature has been very busy lately. And some of these big white, like that ridge that goes right up there and underneath the lighthouse is a big ridge of pegmatite. These are intrusive rocks. Number 2 in my series of 1, 2, 3. And then the third thing to notice is that these rocks are not straight anymore. That is a curved layer. And if you look inside it, all the layers inside it are curved. These rocks have been folded. How do you fold a rock? It takes pressure and heat and time. You've got all the answers right here among you, right? You can't fold a rock at the Earth's surface and break. I mean, you try it, you put it in a vise or something, it'll like stand back because it'll just fracture and break and explode, right? But if it's at high temperature, which in this case is probably 400 or 500 degrees centigrade, and at high pressure, deep in the Earth, rocks fold. Well, we've never been there. We don't know. It's deeper than anybody's ever drilled. But here we can see it. It happened. And one of my wise professors once said, if it exists, it's possible. I miss Leo. Yeah. Look. Look. Did you notice that the last time you were there? It's crazy. If you didn't quite see all the layers, I traced some out for you. Sand and silt is not deposited on the ocean bottom in that shape. Something's happened to it. Even the little igneous rocks got these little folded shapes in them. And if you see some of the igneous rocks intruding this layered rocks, they're all folded up together. Some of these igneous rocks are stretched out, almost coming, they are coming apart. Look at that, little bits and pieces all stretched out. Ah, this is my favorite. Oh, I'm not supposed to have favorites. This one rotated. It twisted like a propeller caught in the weeds. See that layer kind of get twisted up around here and then it goes off this way. And then this will get twisted around this way and goes off that way. The rocks on the top move to the left. The rocks on the bottom move to the right. And this thing rotated like a pinwheel in the middle. Fantastic. I mean, this is just fantastic. Rocks.
Would this have been a sudden event?
No. Yes, I know. This is a great point. This does not happen suddenly. We have seen some rocks where, so if this deformation happens fast, the rocks get pulverized, they get granulated, and we know what those rocks look like. They don't look like this, because the integrity of these rocks is maintained, so you can still follow these layers around. So they must have been soft and squishy, like taffy, and they maintain their integrity. So this happened relatively slowly.
Any sense what period of time it would take that rotation?
Yeah, I don't know. See, we get just so far, and then we get to the mystery part. I don't know.
How did they get to the surface?
I'm only on slide 29. So, how do we put together all of this deformation, all of these different things? Well, here's a guy that figures it out. Mark Swanson. He's a professor at the University of Southern Maine, and he's showing a bunch of geologists what he did at Tule State Park in Cape Elizabeth. He mapped out that whole exposure on a big piece of paper. It takes a table and a half. All the details. Every little fold, every little extension, every little thing. That's the only way you're going to figure this out. You have to map it. You have to see how it's all related. He's really a genius, this guy. He's been doing this up and down the Maine coast for 35 years. And he's done it here at Pemaquid Point. He took digital, now he's gone to high resolution drone photos. So this is that outcrop, and this is the edge of the trees that we're not talking about. And this is that ridge of white pegmatite. And here are the layered rocks. And here are some of those little intrusions that kind of pulled apart. And so he's made this very detailed map. And if you zoom in on it, you can see some of these little white rocks and some of the folded ones. And he's put it all together. You don't do this in a half a day. This is weeks of work. But what you discover is that some of these little intrusions that now stretch out over almost 300 feet, if you put it back together, it was 100 feet long at one time. These rocks have been deformed immensely. And if you look at the ones that have been stretched out, they're more or less perpendicular to the ones that have been folded. So it all really makes sense. And this is his artwork. This is what he wants us to see. This is a map of that outcrop, showing that there are some folded things and some extended things. And if you sheared the whole thing under pressure, you can generate all of those beautiful features that you can walk on today. So we end up with a geologic history just from this outcrop. Sedimentation in an ocean basin 425 million years ago. Intrusion of granite and pegmatite. We can still see them there, but they're deformed by folding, stretching, and twisting. Well, you'd think he'd be happy with that. He's got it all figured out. Well, yeah, but Maine's a big place. So let's look at this map, the one that we got up on the wall here. So at the scale of 50 miles across, we see the same thing. These layers, they're colored now in yellow and green and blue. Different sedimentary layers, different ages. And they're intruded by these rocks in pink, these intrusive rocks, igneous rocks. And then they're all folded up at the scale of the Earth's crust. If we look in detail down at the southwest corner of this map, so from, say, Harpswell Sound to Sheepscot Bay, you see these rocks in yellow are on both sides of this rock that's colored in green? How do you get the same rock on both sides? Well, there's a line right here that we've drawn a cross section. So if you draw a cross section on there, a vertical cross section through, you can see, well, they're tilted to the east on this side, and they're tilted to the west on that side. And before this whole thing was eroded, they used to connect up over the top. There's a big fold here. Just like the folds that we can walk on out here, the folds that we can see, except that this one is a couple of miles across instead of a foot across. So that cross section is showing us the same kind of deformation of the earth that we see at Pemaquid Point Lighthouse Park. There's another cross section north of Booth Bay. Notice the scale on this. We're drawing these vertical cross sections through the Earth's crust, the part that hasn't been eroded yet. So up in the air, we reconstruct the part that must have been there. It's gone now. This is going down to 3,500 feet below the Earth's surface, so 3/4 of a mile. And the rocks are just all beautifully, creatively folded in these wonderful patterns. Well, how can this have happened? Well, we're not the only geologists working on this. There are other geologists in Britain and Scandinavia and down in the Amazon region, South America. And so we get together once in a while, and these are the kind of diagrams that we come up with. We have to put the pieces together. And so 460 million years ago, the world looked different. The Atlantic Ocean, of course, hadn't started yet. It's only 200 million years old. So, the idea that this ocean that we're talking about that deposited the Bucksport Formation, it's not the Atlantic. It was some other ocean that existed before the Atlantic. And here it is, this ocean that was between two continents that we are not familiar with, Laurentia, which would end up being the core of North America, and something called Gondwana, which was at the South Pole, which has pieces of Antarctica and South America and other things attached to it at that time. And in between, there were all these bits of island arcs. It looked like the Philippines does today. And this is the ocean basin where those rocks out at Pemaquid Point were deposited. And every once in a while, there's a little volcanic eruption out of one of these volcanic islands. So we see those volcanic layers in among the sandstones and silts. And as this went forward in time, there was subduction, these oceans closed, these things came closer together and eventually collided, and we get continental collisions. This is a cross-section of what that continental collision might have looked like, where that continent from outboard across the ocean collided with what would become North America on this side. And these little sediments in the middle that used to be out in the middle of an ocean now got mashed in between. And that little red splotch there that's buried in the middle of a mountain system are the rocks that ended up at Pemaquid Point. Igneous rocks are forming by heat coming up from underneath. Deformation is being formed by the pressure of this continental collision. And that's how we understand the things that we see. So these are the kinds of things I have in my head when I go out to Pemaquid Point. This is what I see when I look at those rocks. I see ancient oceans that no longer exist at 30 degrees south latitude in an ocean between continents that don't exist anymore. and I see continental collisions among island arcs that no longer exist, but that we can find remnants of if we look around the Appalachians in South America, up through North America, over through Newfoundland, and across into the Scandinavian Caledonies. All right, so somebody asked, how did it get to the surface? Because here they are, right? If it exists, as possible. And the trouble is, there's no record of that. We don't have anything in the geologic record that tells us how it got to the surface. All we know is here they are, because the 8 or 10 miles of rock that used to be above it is gone. It's been eroded away. Well, there were 350 million years to do that, so it's not impossible to imagine, but it's another one of those things we don't really know. But somehow, I want you to really appreciate the fact that the rocks that we're walking on didn't form here. We're walking on rocks that formed deep in the earth. In fact, the whole coast of Maine, all of these rocks formed deep in the earth. This is an eroded landscape. A deeply eroded landscape. And not just by the last ice age that took a few tens of feet off by glacial erosion, but by miles of rock that's gone off the top. Yeah, so this is the core of the old Appalachian Mountains, and you have to go to the flanks of the Appalachian Mountains to find the debris, which would be the Catskill Mountains over in New York State and Pennsylvania, or over into New Brunswick to what they call the Maritimes Basin. So there are sedimentary deposits with a lot of erosional debris, but you have to go a long way away to find it. Yeah. In the same way that the Himalayas today are eroding, but in order to find that debris, you have to go south of India into the Ganges Delta to find all the debris. There it is, but it gets transported a long way away. Yeah. I love these questions. Yeah, you're geologists. Yeah, you didn't know it, but there you are. All right. And so this is where I want to recognize this wonderful map that, I brought a copy if you want to look at it, that I just discovered that the Penobscot Nation put out. It's called "This is How We Name Our Lands." And of course, the Wabanaki had a lot fundamentally different relationship to the earth than we have. And the names, so they put out this map with a concerted effort among all the elders to see if they could recover a lot of these names for the places and translate them. And some of that information, of course, is lost in the oral tradition. But Sebaska Deegan is a place that we might know. It means almost through passage. And Sheepscot has nothing to do with sheep. Sheepscot means many rocky channels. And if you know the Sheepscot, that's appropriate. Madomic is a place of many alewives. And Pemaquid is the point extends far out. So these places are named for what they are. They have seen these places, and this is what these places mean. Well, Shelley Gallagher is here tonight, Director of Parks and Recreation in the town of Bristol. And she has a great job. And she knows it. And she loves what she does, and she can't wait to tell everybody about this park. And she called us last spring of last year. Said, I think you guys might want to come down and look at this. So there's Shelley and there's Steve, who I will let have a chance to talk if I don't run off the whole time. And there's Shelley's rock right here. This rock, we're looking end on. This is a big piece of pegmatite. And it's not where the last place is that I remember seeing it. It belongs up on this ridge where Steve's hand is. That's where it belongs. I have a photograph of it on our website, of Pemaquid Point website.
In the sense it belongs, why doesn't it belong where it is now?
Well, so this is end on, and here it is sideways. That's 40 feet long. That's longer than this house. Yeah, Shelley, we were interested in that. Steve's a marine geologist. He's been studying coastal processes for his whole career and before. This is where it came from. Shelley's standing on the place where it came from. We know that. And there were some smaller pieces too. Some huge smaller pieces that went at the same time. Now the interesting thing here is, well, there's all kinds of interesting things. But right here, these dark colored streaks, those are quartz veins that we're familiar with from pegmatites. They're common in a pegmatite that's been deformed. And here's some of the metamorphic rock that's attached to it. And if you look at the place that it came from, here are the quartz veins in that pegmatite going this way. And if you look at where it came from and where it is now, they're not going the same direction. This rock has not only been turned upside down, so this is the bottom of it. It belonged here. It matches right up. We could put it right back if we were strong enough, which of course we're not. It's flipped over and it's turned sideways. And this rock, which the first time that we saw pictures from Shelley, it was here in March of 2024, is now over there. So it's kept moving from storm waves. And if we go look at that little one, it's flat on the bottom. It came from up here on the ridge. And we can put it back because if you look closely at this end of it, it matches exactly with the rock that's still in place where it came from. So where it is, where it was. So there's no, we've got the forensic evidence, if you will. There's no question what happened here. What we want to get across is the immense power of the ocean, especially the folks that might only be here in the summer. So this was January 10th, 2024. And how do we know that? Well, this is when I turn to Steve, because he's the marine geologist, so he's going to tell us what happened.
Hey, good evening. Thanks, Henry. Yes, what happened? I've been studying erosion on the coast of Maine, coastal processes, waves, storms, things like that, for over 30 years. And right here, right down the street, is the biggest rock moving event I've ever seen here in Maine. Okay, so you guys are in first place, and you can go down there and you can touch it and you can, push on it if you want. Or you can play Puzzle Master and try and recreate what you're looking at down there, just like we did. And it's actually, now that you've had this intro by Henry, you know what you're looking for. So what I'd like to show you is what Shelley said. You guys should come down and see this. Because Shelley had braved January 10th and went down to the water and took videos. So the rock, if I can get that laser pointer, this is the rock that's the granitic pegmatite that Henry was talking about that moved. This is where it moved. While it was moving, she took this video. This is not where it started, but it comes from here on down to here. And you can see the ocean. Monhegan is out there in the distance, right? This is a southeaster. The swells are coming in from Monhegan, pushing straight up the peninsula parallel to the layered rocks and dumping over. So we'll show a short video clip of the swells. You can see the giant troughs and the crests and the waves here coming in and smacking at these rocks. So I'll start the video. Line and up and over. We have another video, courtesy of Shelley. Watch it one more time. And then, for a frame of reference, you know the bell tower. And it had already suffered quite a bit of damage by the time she was there taking this footage. Let me see if I can play this video. So you can see why the bricks didn't stand a chance. You know, they just power the waves, the height, the one up, and that was just a single wave. So this has happened over and over again, especially at high tide. Shelley, you're pretty close.
I will totally admit I was too close. Any videos on the third one?
So here's the last video, and you can sort of see the bell tower right through the bell tower. And now you know why the bricks and everything in the foundation had to be repaired. So we'll show that one more time just because it's pretty darn rare footage. So I'll put this storm in a little context for you, a little bit about the past storms we've had. Some of you may remember the blizzard of 1978, took out my grandfather's dock. All of this information that I'm going to quickly run through is available to you in much more detail in this report called the Scientific Assessment of Climate Change and Its Effects in Maine. And the 2024 update is the newest. It's a little over a year old now. But this was a team of 30 or 40 scientists that put this together. I was one of the editors, and I was involved in the sea level and coastal storms section of this. But it's online at this website, and it's a compendium, not just of geology, not just of oceanography, but of biology, plants, trees, and everything else related to climate change, precipitation, wind speeds, things like that. So on January 10th, out at Monhegan, there's a buoy. It's the green one. I'll go back to my pointer, I guess. The green dot out there is the Monhegan buoy, and you can, there we go. You can check out the waves any day, even from the hurricane recently, and see how high the waves were, and you can make graphs and so on of it. So in Monhegan, on that day of that storm with the footage, the waves were 30 feet high. The perfect storm in 1991 had 30-foot waves. The Portland buoy, which we often listen to as mariners, talks about how big the waves are, what the wind speed is, and so on. That broke its chain and went out to sea in a 30-foot wave. The Monhegan buoy survived, and on the only 3 days later, the waves were 25 feet on the 13th. But it was the wave action, obviously, that was bigger and moved the rock around out here the most. But as Henry said, it still keeps moving. Shelley says it's been moved again. The Portland storm surge, the tide gauge measures the tide levels, and there's a predicted tide, and then there's the surge, the amount that the storm is, coastal flooding is coming in and adding to that. And that was in the range of 2.7 to 3.3 feet on both those storms. That's nothing too extraordinary. Every year we get a foot of surge up to 2 feet of surge. So it's a little bit higher than normal, but the biggest surges in that tide gauge, which so far have not come at high tide, thank goodness, are 4 to 5 feet high. So the worst case scenario isn't even what we just saw in the video, if it happens to have the biggest surge in the historical record. Anyway, this was so big, as you can see, it cost $70-some million in public infrastructure damage. In addition to that, a lot of private structures and waterfronts and property were damaged in that storm. So it became a federally declared disaster. So I'm going to show you just a few more sciencey, graphy things, but this bar charts here show the tide height in Portland, here, Bar Harbor, and Eastport. So each of these bars is a different storm event, and we kind of call it the Olympics in the office, kind of a joke, but what place is this storm in, and so on. And so the blizzard of '78 is the storm here under this column. It reached 14.17 feet because it was an 11.27 foot tide. It's a big tide. People nowadays call these king tides. It's a perigean tide. And there was a 2.9 foot surge. So the numbers in red are what we stack on top of the everyday tide to get up to 14.17. And on the 10th, we had a smaller tide, 9.88 feet, but a 3.2 foot surge. So they stack those together. And then, because the ocean's been rising, we can add 0.63 feet more on top of that to give it a little nudge. It's kind of like getting on steroids here in the Olympics. The 13th was even a bigger tide, 11.2, much like the blizzard of '78. And the 2.7 foot surge was substantial. And a little bit of sea level rise again, and we get up to 14.57. That's first place. That's the gold medal in Portland. And that was the storm, the second storm that kept moving the rocks down at Pemaquid. So the other graph I want to show you real quickly is what is sea level rise doing and what might it do going forward. So this comes out of our report, and the little graph up here shows in black the tide gauge in Portland. So this is what the tides have been doing. They vary from year to year. They vary from season to season. All this kind of information is going up and down and up and down, but it's kind of a little bit like a financial markets, it's going up in a long term. And the best computer models and projections for the future go from 2020 out to 2050 with a rise of as much as 1.5 feet in high tide by 2050. Now that's only 25 years from now. And down here we look at the longer historical trend from the tide gauge going in back in 1912 all the way up to a projection of 2150, so 125 years from now. And that little box up here is this inset. And we looked at different scenarios, and the numerical models are low, which means we don't really have more carbon emissions of significance. Interim, sort of the middle pathway, which with greenhouse gas reductions, we kind of follow that. And high, which is this red curve, is business as usual. The approach of we don't get emissions down, that's maybe where we'll end up in 2150. So this graph is also comparing what we did in the 2020 assessment, the first one, compared to the second one. And we've bought ourselves a little more time because we were projecting here, but it's not quite as high. It's a little over a foot by 2050 in this scenario, and that's the median. I mean, you could be plus or minus the band. So we've maybe stretched out the time frame to gain a few more years, a couple decades, in the most recent modeling. But there's much more detail on this in the report if this is the sort of thing that you're interested in. And then the last graph is one that shows in each of these bars are the number of hours in the course of a year that it flooded in Portland. So if some of you are watching in a winter storm to come around, and the camera crews from channel 13 and 6 and 8 all go down to Jay's Oyster Bar, because a 12-foot tide, the king tide, the highest tide we get is 12 feet, and anything above that is considered flooding. So these are the hours above flooding in Portland since 1912, when the tide gauge went in. So if you look over time from the left in the past to most recently 2023 data, we can kind of see there's a big shift to more hours per year. So we used to have an average, if we take all of the data and average it, we have about 4 hours per year of flooding. So that's not too bad. And you know, a winter storm, a northeaster, might just account for all of that. And then we get up to 10 if we look at the data since the year 2000. And if we just look at the last 15 years, 2010 till now, we're seeing 12 hours per year. And this doesn't sound too bad. It's not too dramatic. Those can have caused some significant waterfront damage on those few hours that the water gets up that high. But if we were to raise sea level just 1 foot, those numbers would just go right through the roof. And we talk about some of that in our report too. So sea level rise and coastal flooding are interrelated. The trend is upward, and even a foot of sea level rise will probably cause a great amount of additional damage. So we know more storms are coming to Pemaquid. So I encourage you, and I'm sure you will now, because you've got your geology goggles on, to keep visiting. Look for the geologic history that Henry is giving you a primer on in the rocks. The coastal processes, you can stand where those waves came, but you don't have to do it on a wave day, right? You can go on a nice sunny day like yesterday, today. The coastal processes will continue. I mean, they've been continuing for thousands and thousands of years around this elevation. And you can watch for further changes. And there's no doubt change is still happening right down here. So you can do it any way you like. You can make a sketch, you can take pictures, you can go to the same spot over and over again. You can look back in your photo albums and see if you had some back then that show where the rocks were, and then you go take the same, find the same place, take the same picture. So there's much to see and to enjoy, and I think you'll too start enjoying the geology. So lastly, in closing, if you're curious, want to know more, come visit us online at the Maine Geological Survey website. It's easy to find. You can find all kinds of things there. We have videos, we have educational information about how did Maine get this way. We have something you might be interested in called field localities, and you can open that up and you can get a map, and it's interactive, and you can say, I'm going to go over this way, I'm going to Belfast, what can I do there? And you can get 8.5 by 11 printouts of like what you can see, where you can park, things you can do. And it'll be like Henry's little short course here on what you're looking at when you get there. So the field localities are great. My colleagues and I have put in a sea level rise dashboard. It's much more timely and accurate. It's like a ticker. We call one of them a ticker. So you can sea level rise after about 2 weeks into the new month. You can see where sea level rise in the preceding month. So it's really up to date. You can see all the statistics, the averages, and the trends. And you can explore other aspects of Maine geology too. You can go delve into what a granitic pegmatite, your state rock, is. Have a look at that. You can learn about mineral collecting, you can learn about landslides, you can learn about aquifers and water, all kinds of general information that's even useful as homeowners. So come visit our website and have a good time doing it. I've retired, so you can't call me up anymore. Henry's retired. You only got a month, and he's got a lot to finish in his last. But there are other colleagues at the Maine Geological Survey that will be absolutely delighted to work with you. So Henry can find everything historical out there. Look at this. This is 1910. And we started out, we didn't show you this one in the beginning, did we? 1910. Well, you know what we're looking at, don't you? It's what I'd like to call Shelley's Rock back in 1910. Here it is. And it's down off the picture now. But these early photographs, historical information is extremely useful. And when you talk to me, I'm like, those rocks, they're never going to move in my career. Well, they did, you know? So more power to you. Go out and take a look and have a look around. And with that, we can end it right there. And if we have time, maybe some people have some questions. But thank you very much.
It was solid, they were solidly attached. They weren't just sitting there, but there are fracture surfaces in these rocks. So when it broke, it took advantage of the natural plane of weakness. So that's a kind of a in-between answer for you.
But there weren't cracks, so
There were cracks, and there are still cracks. In fact, if
they
you,
weren't solid cracks like the rock was sitting on top.
it wasn't just sitting there loose, that's right. That's right. It was attached, but there are fractures. In fact, if you go back to the place where they came from, you can see some of those fractures extend into the rock that's still present, that's still attached, but the crack doesn't go all the way through. But the next time, it's probably going to expand on that existing crack till it opens it up more.
And I just want to emphasize what you saw them present tonight is a tiny portion of the work that they've done in the last 50 years. I mean, the amount of knowledge that's available to you, to the layman, is just mind-boggling. It's so much better than the other cities and states in New England. These guys are great. Give them a hand.
Thank you.
Do you put these projections into your flood map projections? Because our cottage is below regular flood level, and what you're saying is it's way below projected level. So do you do that on the floodplain maps, or are they just based on present day?
Yeah, the federal FEMA, Federal Emergency Management Agency, produces the National Flood Insurance rate maps that are used to set flood insurance policies. And they show you the flood zone boundaries, and they do not show you the future. They don't add on sea level rise. There's been a lot of discussion about we need to do something like that, but their program has had difficulty producing updated maps. There are parts of the state that don't even have good flood maps in them. But no, they're not there. So then if you took a flood elevation off that map and you want to say by what year, 2010, 2025 or whatever, you could add it on. But there's also the V zone, the velocity zone, the surf zone, we saw that in the videos, that is not static. You can't just add a foot to that. So it gets more complex as the waves run up. So no, the flood maps don't take into account even the last decade or so of sea level rise.